So yeah, my name is Jonathan Fernsler. I'm a physics professor here at Cal Poly, and I became interested in epidemiological modeling a year ago, like many people did, because of the impacts of coronavirus. And so today I'm going to talk with you about a student project I've been working on for the past 5 months, where we are using particle simulations of epidemics as a way of testing out some of the dominant models that are used today by the groups that contribute to the CDC forecast. And those students, I just want to go and name them because, and I see some of them are in the audience here. I've got Julianne, Peter Lentz, Alexis Morris-Solik, Madison Singleton, and Patrick Sullivan. I also want to call attention to my father, Richard Fernsler, who this is the first project we've ever been able to work on together. He is a physicist as well, and he worked on with me for the last year on the theoretical background to the project. So it's been a really neat experience. So we have a short time, and we actually have a large number of conclusions we've reached from this project, and some of them we actually feel are provocative and surprising, and we hope this will trigger some conversations with the epidemic modeling community. And so I'm going to jump right into our main conclusions to start my talk, and then I'll go and take a step back with the time we have left to go and do a little more background. So what we did was to simulate epidemics using particles, where each particle represents a person. And we can classify those people's relationship to the disease as people who are susceptible to the disease. And he'll run our little simulation here. And if a susceptible person comes nearby a infected person in red, then there's a probability chance that they may become infected. This is determined by a random number generator to see if that propagates. Those people then become infected for a certain amount of time that we can set in our simulation, and then they become recovered and are no longer infectious. So a very important other aspect of modeling these diseases that we found is that people's infectiousness changes as a function of the time after they've been infected. And so we can represent something like this as a probability of infectiousness type function, which is again, after the time that they've been infected. And this type of function has been measured for COVID-19 using contact tracing data. And we can generate a simulation then that reproduces this type of behavior. And so this is kind of like an actual modeled coronavirus mini epidemic. So what we wanted to do with these particle simulations was to compare some of the main models that are being used today to predict the coronavirus infections used by the CDC. And the dominant model that I've found from surveying the CDC website is the SEIR or SIR models. And these two models are very common and are used by many groups. We wanted to compare this to a second model that I'm coining as the general infectiousness model. And this model is much less well known, although it turns out that its historical roots are just as old and possibly older than the SEIR and SIR models. And so we believe this is a first comparison that's been made of actual solutions to these models in the literature. And so we're hoping to finish writing this up and publish this hopefully in the near future. So the first thing that an epidemic model should be able to do is to predict the infection rate. And this is similar to the daily new cases you see reported from Johns Hopkins. So what we did with our project was we used the early data to our simulations, our particle simulations, and then fed them into these two different models to see if they could predict what happened in the future. And we used all the standard tools that are used in the literature by the main CDC groups. So our particle simulation here is shown in red, and the SEIR model would do a reasonable job with some of the predictions, but when a change was simulated, then they often did much more poorly, like this one where we're simulating wearing of masks. On the other hand, the general infectiousness type of model was able to adapt to those changes and generally did a better job simulating or predicting the infection rate from the simulations. The other thing that an epidemic model should be able to do is to predict the fractions of the population who are in these susceptible, infected, recovered type states. And so again, we can do this with our particle simulation and try predicting it with the different models. And again, we found that in all the cases that we have investigated where we expect these disease models to be able to work, the general infectiousness model did a much better job at predicting the data than the SEIR model, which is surprising because it is much less well known. So we believe that there are some significant flaws to the SEIR models that are being used. And we believe that there is a simple fix because the general infectiousness type of model is actually just as easy to implement. And our students wrote the code for all of these. So these are absolutely applicable types of models that can be used. Okay, so with the time I have left, I'd like to go and give a little background to epidemic models. So epidemic models are mathematical tools that are helpful for governments to plan the future impacts of an epidemic like coronavirus. And here I'm showing the IHME lab model for California. This is back in December. And they predicted a peak in infections over the winter months. Of course, we indeed saw that occur in California, and it had huge impacts on the state and around the nation. So they are using an SEIR type of model, as I described. When I've surveyed the CDC website, they use many different models, 29 in total, and the dominant model by far, there are a variety of models, but the dominant model is this SEIR type rate model. And as an example of that, 6 out of the 7 models are used by the CDC that use social distancing changes of people, basically changing people's behavior to predict the future outcomes, are SEIR type of models. So these models, just in a very brief description here, can be, they automatically classify the population into those categories of susceptible, infected, and recovered. And they use the number of infected people to predict the future infections. They do this by using these parameters, rate type parameters, that are related to the famous reproduction number R0 that I think probably everyone has heard of in the media at some point. So these rate parameters are similar to, can be thought of as like little knobs you can turn to go and adjust how people's behavior could change and then predict how the model will adapt to it, like people wearing masks or social distancing or quarantining, etc. These parameters must be interpreted from the infectiousness probability function, and they use fits to the infection rate data to seed the model. So our students were split up into 2 groups, where we had one group of a particle group that ran the simulations in a variety of different circumstances. And you can do all sorts of different things with these simulations that can try to mimic the behavior of real people. The second group, the modeling group, then took that initial data from the simulation, which is comparable to the daily new cases you see here from San Luis Obispo County. And here's some example data right here. So for the first 10 days of a simulated epidemic. And then they use that to try to go and predict, using standard procedures in the literature, the next 90 days, say, of the epidemic. Okay, so I'll leave with one last little case study to show again what we're talking about. And for this one, we looked at the impact of population density on the spread of an epidemic. So if we compare early data from the coronavirus epidemic back in February and March, New York had a very rapid rise in cases in comparison to a state like Wisconsin that had a much slower growth initially. And a lot of this can be attributed to the difference in population density between these states. Later on, as an epidemic progresses, then other behaviors can be more important. But initially, a lot of this is attributed to things like population density. So we can go and simulate this with a particle simulation by just reducing the density of the simulation. And we think that a good epidemic model should be able to predict the differences. So if we run this with our SEIR model, then we found that it had a reasonable simulation or a prediction of the urban situation. But if we try to go and use those parameters to figure out what we think would happen in a rural simulation, then it was much more poor. Similarly, it undercounts the peak number of infected people in all of our simulations. So what we found from this is that the SEIR model is flawed because the parameters that seem to be simple rate parameters are actually more complex. They are not independent of one another. So if we change the reproduction number, then in order to predict the future of the epidemic, one must also change the recovery rate, even though the particles in our simulation were infected for the same amount of time in both simulations. Okay, so it's a more complex kind of interaction between these parameters than it first seems, and this we believe could lead to a lot of errors being made. So in closing, our general infectiousness model, we believe, is a fix for these flaws. And this model uses that probability of infectiousness function directly to the infection rate data to predict the future. And we found that it worked better than the SEIR and SEIR models did in all the cases that we have investigated. And if we go and compare those results, again, we can see for our population density simulations, it does a significantly better job, and it adapted to those changes. Notice, by the way, that the number of infections here is actually much lower for the rural simulation than the urban one. And again, also for our population fractions. So in conclusion, I'd just like to say that it's been an interesting project, and we believe we found some serious problems with these dominant models, and we'd love to engage in more of a conversation with people in the epidemiological community about these things we found. Everyone is inundated right now with different models and ideas, but we'd love to go and talk more about these findings. And also just want to thank my students. They did an incredible amount of work in 5 months' time. They learned a ton about modeling and programming and other issues. So thank you very much. I appreciate any questions.
Thank you very much. That was a great work by you and your students. And so we have a few minutes here. We have time for some questions or comments.
One thing I've wondered about with a lot of these models is to what extent they incorporate heterogeneity in the population. Do your particles have different collision rates, or can that be built in?
Great question, Jason. Yeah. So all of these, the models that I've been investigating assume a homogeneous population. Okay, and those are the ones that are actually used by these CDC groups. Now, the way they tend to do it is they'll break up the population into usually the county-based, just as Johns Hopkins does. It breaks up into county-based reports, and basically the assumption is that within a county that it's a relatively homogeneous population. But you're absolutely right. What's something we would like to investigate in the future. We haven't been focusing on that as much yet, but we'd like to go and investigate what happens with our particle simulations if, we have it where it's more heterogeneous, it's not homogeneous. And so we can easily do things like this by slowing down the particles, for instance, and you just have little pockets of infection that will go and spread in one region, or you could have more complex interactions as well. So that's something for the future for sure.
Great, we're almost out of time here, but Dr. Fernsler, I just want to add a quick question. Can you use this model You said for infectious disease, we can use it for other diseases like chronic diseases. Maybe the social exposure, would the same principles apply for that?
Yeah. What's really neat about these models is that they are applicable to a really wide variety of circumstances. And for instance, like the sort of seminal paper that brought mathematical modeling, epidemiology into the biology community is a paper in 1981 by Anderson and May, and they actually use this for the study of microparasites in insects. And that's then became the seed to use it for diseases in humans. So yeah, there's a wide variety. These things are can be thought of in a mathematical kind of way, and so they have wide